So today we're going to talk about Hnmr. There are 4 things to consider with Hnmr. The first is the type of hydrogen environments. Normally I'd say this is going to lead to the number of peaks. You have to be careful though as to what's defined as a peak, but generally speaking, yes. Each of these is going to define how many peaks we have in the NMR. Then we have to talk about the peak location. Where is it going to be on the spectra? And like most spectra, you have an X and Y axis. As we talk about things, this is going to be downfield, and this will be upfield. And our normal spectra numbers, we're going to have about a 0 right there. It depends on how far downfield you print your NMR. Often it can be up to 14 or even just 10. So it's a relative type of thing as to what you're looking at there, but that's what we normally have. The next thing we're going to look at is the integration of peaks. And finally, where I find a lot of people get a little bit confused, which there's no real reason to get confused with, it's in the splitting patterns. So splitting patterns we definitely need to look at with more detail. Okay, so let's go into the first thing, which is our hydrogen environments. So in this section, what we're trying to do is we're trying to identify the different types of hydrogen that exist in a given molecule. Now, NMRs are very, very sensitive. They can pick up just minute differences depending on the strength of the magnet of your NMR. Now, I'm not going through the theory behind NMR. I'm going through how to actually read NMR spectrum in this video. If you want to know more about the theory of that, I would certainly encourage you to check that out. But for right now, what we're trying to do is look at the different types of hydrogen environments and assume that we've got a magnet that is strong enough to be able to tell the difference. So right here, I can tell that there's a hydrogen. There's no other hydrogen like it, so that is going to be a peak by itself. The other thing that I tend to do when I'm looking at looking for a spectrum or analyzing a spectrum is I go through and sort of put where is it that those hydrogen are located. I like to use dots just because I'm too lazy to draw out hydrogen. So that's totally fine if that's what you want to do. So I would say that this is one type of hydrogen here. This is another type of hydrogen here. And then a third type of hydrogen here. So we have 3 different environments. So that will basically lead to 3 types of peaks in my NMR spectrum. Okay, on the next example, we would have 3 hydrogen on this one, 2 hydrogen here. Keep in mind, this next carbon here does not have any hydrogen, but the last one over here does. Now, you may say, oh, well, those are the same over here as over here. No, they are not. They are not. Because this oxygen exists next to the ones on the right versus the ones on the left do not have that. So this would be environment A, this would be environment B, and this would be environment C in this case. So there's still 3 different types of hydrogen. That's not necessarily the case for everything. Obviously, on our next example, we have a hydrogen right there. When it comes to benzene, even though the double bonds look as if they are localized, keep in mind that's not really the case. When it comes to a benzene, a lot of times we draw a circle there because resonance is constantly happening. That's part of the reason why you'll see me abbreviate benzene like this quite often. Because right now, the way that I'm looking at this, keep in mind, there's hydrogen here. There's a hydrogen coming off of each of these positions, right? They look like, for example, that these 2 hydrogen are different. They are not. They are the same. only because of this resonance. If you actually had a molecule, let's say that we have a double bond here and an OH. At that point, yeah, this hydrogen is different from these two hydrogen because this guy has a double bond and these do not. Those would be different. But in a benzene ring where we have resonance, both of these carbons are next to a carbon with an OH to it. And so those two hydrogen are equivalent. Okay. Now the next two hydrogen are also equivalent. And then we have this one by itself that's over here. And yes, each of those are going to be different. So I'm going to keep with what we've been doing and label this A, B, C, and D. Okay. We do that better job there on D. Okay. Just a second, let me clean this up so that we can look at this last molecule. So this might be a good time for you to pause the video and go, I want to see if I can figure out how many different types of locations we have here. So assuming you may have done that already, let's go through and try it. We've got 3 hydrogen here, we've got 2 here, we've got 3 hydrogen here, and I just have 1 here and here. Well, interestingly, we have some symmetry in this molecule. So if you look straight down the middle, that is a mirror plane, which means that we actually have similar types of environments. So I would say that this and this together, both of them, are A. These two are B. And this one I would call C. Now, if you label that differently, that's totally fine, as long as you've got the 2 A's are the same, like you've got them labeled as the same signal, that would be correct, and then the B's the same way. I want to go back and state one more thing on this benzene ring. It is the case that you should have A, B, and C with different peak locations. Let me say an if you have a strong enough magnet. And if you can zoom in close enough on the spectrum itself. And realistically, a lot of times those peaks will overlap each other. I'm going to show you an example where they kind of look like they're overlapped, but if you zoom out a little bit, you can sort of see that they're defined on their own account. But oftentimes those do tend to run together. Luckily, when it comes to the peak location in a benzene, you can tell where those are located pretty easily. Okay? So next, by now you're familiar with the term electronegativity. Remember, electronegativity is the pull of electrons towards a particular atom. Well, when it comes to NMR, when we're looking at the nucleus of different hydrogen, having electrons pulled away from a hydrogen, or what we call de-shielded, is going to change where those peaks are going to be located. So, in general, hydrogens that are closer to something that's electronegative are more downfield. So remember, downfield is that way. And if you're not next to something that is electronegative, you will shift further upfield or closer to 0. Okay? So for example, the hydrogen that we see in this first problem, that might be located, from the OH in this first problem, in the 2 to 5 region. Okay? So most CH3s or CH2s, CH3s are in the 0.9 range, and the CH2s are in the 1+ range. So the fact that that CH2 is right next to an OH might move it a little bit further up, okay? Or, sorry, up in number, but closer to downfield. Those terms can get a little bit confusing. So when you see the actual spectra here, what we're going to see is we're going to see a peak at 0. Now that is our way to sort of normalize things. That with TMS, which is tetramethylsilane. It's an additive that we put into our samples so that we can see where 0 is located. You're then going to have peaks at the 0.9 range, and that's going to take on a certain type of peak. And then we'll have one at the 1 range, and then we'll have another one further up at the 2 to 5 range. So you're going to have different peaks there, and that's what I'm talking about when I'm looking at an NMR. On the second compound, we have a different set of criteria as well. In the next example, we see that there is both B and C that are located next to oxygens, kinda. Keep in mind that this carbon is directly attached, this carbon's directly attached to that oxygen, which means that the oxygen is pulling electrons this way more than what we have happening at B, because B is connected to another carbon that's connected to the C double O bond. So that means that C will be further downfield. So this is the furthest downfield. This would be sort of in the middle, and this would be the furthest upfield. And by furthest, I mean we could have this come in at a 3 or a 4. It's not good that it's going to be massively high. It could even go up to 5. Okay, next on our benzoic acid. Obviously, this OH should be pretty far downfield. Now, since we're dealing with a phenyl group, then the place where the phenyl group or benzene comes in, those peak locations, are between, all of these hydrogens are between a 6.5 and an 8, usually. What that also does is it changes where that OH is coming in. As a matter of fact, on this particular compound, that's coming in around a 9. And part of the reason for that is that in a benzene ring, you have the electrons that, again, are being delocalized here. So the electrons are being pulled to the center of that ring. And that's why you get such high peaks in that range. So in this case, I can tell you that these peaks are for C would then come in next at 6.84. This may be a bit unexpected, but this is actually going to be higher at 6.24. And finally, here we would have a peak around 7, so 6.9. Okay, so the reason why those are happening, we're going to go through more in Orgo 2, so you can know sort of where those locations are located. But for now, I want you to know how to read those. You can also see how things can start to overlap really quickly. So the 6.9 and the 6.84 are going to look very, very similar. It depends on how strong your NMR is and how much peak resolution you get there. If you have some type of impurity, a lot of times those are really hard to see in the NMR because with benzene rings, they can stack on top of each other anyway. Okay. In this last example, we're going to have 3 different peak locations. They are all going to be relatively upfield. Vinylic hydrogens, so hydrogens that are directly attached to a double bond like we have in B, are going to come in at a higher location. So these are around 4.5 to 6.5. Now what we have with A in both cases, because that is one peak that we will see there, is that those are an allylic hydrogen coming in around 2. The other one is just a regular CH2, so we'd probably see that in the 1.2 region. Where did I get those numbers? From a chart. That's it. Not doing anything like hocus pocus here. That's just where those numbers come from. Okay, good. That's a lot of data that we've got now looking onward. Integration. Now that sounds like some good calculus, right? Well, yeah. Remember in calculus, what was the point? Well, in calculus, what we were trying to do is we were trying to take the area under the curve. And that's what we're doing here. Those peaks that we've sort of defined where they're going to be located and how many of them we have, now we're going to look at what happens when we integrate them. And so integration is a relative type of ratio. It'll tell you what the ratio is of those different peaks to one another. That's really useful. For example, we have 3 hydrogens in A. So it will show us that we have an integration of 3, B would be to 2, and C would be to 1. Now, if instead you had started off with the hydrogen here, for example, being 0.5, then B might be 1 and A might be 1.5. So these are all relative numbers to one another. But if we keep filling this out, those ratios we can sort of see as they relate to one another, this becomes pretty easy. A is 3, B is 2, C is 3. Again, that could be 1.5 to 1 to 1.5. That's fine too. Those ratios are still the same. In D, we'd have, in the next option, we'd have 1 to 2 to 2 to 1. Again, when it comes to the benzene ring, that is hard to sort of separate those. So you may get sort of a mixture of things there. Okay. Now, A, in this case, since these two are equal, are going to have an integration of 6 to 2 to 2. Since B, those are also equivalent. So you may get this instead as a 1 to 1 to 3, and you'd have to sort of figure out what that looks like. Okay, good. Finally, when it comes to splitting pattern, I'm going to keep this simple and just give you these 2 examples for now. And then as we go through examples, and as you go through more examples, working through them on your own, you can sort of conquer some of the more complex patterns. So here's how I look at splitting patterns. The people in my house may not make me have a headache, right? The kids in my house may not give me such a headache. But when it comes to the neighbor's kids, oh, now that can give you a headache. This is how I think of things, you all. My neighbors don't actually give me a headache. I'm just trying to relate it to you in a way that makes sense, okay? So when it comes to the splitting pattern for Hnmr, it's not the hydrogens on the carbon that you're looking at that will cause that to split. It's the ones that are located next door. So here's what I mean by that. Let's look at A in this case. Now we've already done the integration. We know where those are located. But these are going to be an integration of 3 on A, but they're split by the ones next door in a pattern of N plus 1, where N is the number of hydrogen that are located next to that particular peak. So we would say that this is 2 plus 1. And what that does is that A will then be put into 3 peaks, which we call a triplet. Okay, so you're going to have 3 peaks there, and that's sort of what they look like. Okay. B, on the other hand, is going to be split by A. A has 3 hydrogen on there. That's going to be N plus 1. In this case, N is equal to 3, so we're going to have that as a 4 So that peak is going to look like that. So we call that a quartet. These are very common to see next to each other. What that basically means is that you have an ethyl group. Okay, so that's what's going on there. Now, when you have oxygen that gets in the way, that's got a lot of electrons on it. And so it kind of stops the flow of splitting from next door. That's the reason why I did not count this hydrogen when I was looking at B. So when it comes to an OH, that hydrogen is just going to be by itself. So that's going to be a singlet. Okay. We would see a similar type of pattern over here. So this again would be split by B next door, giving you a triplet. And B would be split by A, giving you a quartet. Okay? And then C, being by itself, is just going to be a singlet. When you have a lot of things that are splitting one another, so for example, if I have a chain, and let's say we've got something like this, the hydrogen that would be coming off here would be split by, we've got hydrogen here and here. I've got 3 hydrogen here. I've got another hydrogen here. So that's a lot of splitting. So at this point, I would call this a multiplet. That just means that we've got lots of different types of hydrogen that are splitting those hydrogen patterns. Okay, so try not to get confused with the splitting patterns. Realize that you can get a lot of information and then attack the splitting patterns. So let's look at some real examples and see what we've got. Here we've got 2 butanone. So in this case, we have 3 hydrogens here, 2 hydrogens here, and 3 hydrogens here. So that means that we know, first of all, we're going to have 3 hydrogen environments. Okay. I just go straight down those 4 rules. We know that that's also true because we've got 3 here, right? We've got 1, there's 2, there's 3. Now we've got to figure out which is which. Note on this particular NMR, we don't see the TMS peak, but it's probably been erased. I want to thank the National Institute of Advanced Industrial Spectroscopy and Technology because these are wonderful peaks or wonderful spectra that I can show you really nicely. So the second thing we need to look at is location. So location, location, location. Remember, we're going to have something that is being pulled, our electrons are being pulled away from it, the hydrogen that are there. And I can tell by the splitting pattern that these 2 are right there. So those are further downfield. This one is right here, and this one is right there, okay? So the third thing is integration. Now, we don't have the integration data here. I could get that, but we know what this is going to be. So our quartet here is going to have an integration of, I was thinking 2 and put 3. So that would be 3, and this would be 3. Okay. And then the fourth thing is splitting pattern. So the reason why I know that this quartet goes to this guy right here is because the n+1 rule. There are 3 hydrogens next door, so n+1 is equal to 4, and that's where our 4 comes from right here. Okay. This is a singlet because he's not next to anything. And then right here, we have a triplet because there are 2 hydrogen next door. So that's where we get this from. See, this works really nicely. Let's do another example. Here we have 2-propanamine. Now, part of the reason why I gave you this is because when it comes to NH2s, nitrogen, keep in mind, has a lone pair of electrons. And if I were to just draw NH3, here's what it looks like. Well, so here's the thing. Nitrogen, with its lone pair of electrons, can electronically flip from that electron pair pointing, let's say, in one direction versus flipping and pointing the opposite direction. So you might have something that looks like this. But it's happening in 3D, and it's constantly happening in 3D. So a lot of times what we see with nitrogen is that these can become broad. So those peaks can become broad. And a lot of times, therefore, we can't see the splitting pattern with them. Sometimes we can, sometimes we can't. And I bet in this one, it's so nicely defined. I see 2 peaks right here. And so that's probably where our nitrogen is. But I just wanted to point out the fact that that can definitely be something that happens, okay? So in addition to that, I have a hydrogen here. I have 3 here and 3 here. And these 6 are the same. So this hydrogen right here, I know that's my multiplet because I'm being split 7 times, right? Because you've got 3 hydrogens to one side, 3 hydrogens to the other. Even though those are equivalent, all of them contribute to the splitting pattern. I didn't say that earlier, so yeah, that n plus 1 in this case is equal to 7. So we would call this a multiplet. Okay. The nitrogen is usually going to come in as a singlet. And then these 2 are only going to be split by this hydrogen next to it, right? These 2 are going to be split by the hydrogen next to it. So we're going to get a doublet, and that's what we see here. So that's going to be a doublet. Now the integration should be that this multiplet has an integration of 1. The NH2 peak should have an integration of 2, and the doublet should have an integration of 6. Sorry, I didn't go through the list as succinctly as I did in other examples. Let's go to the next one. Okay, here we have what a benzene looks like. See how much further downfield everything is located. So our COOH, this hydrogen right here, that's this guy. We then have different types of peaks inside. We've got this one, we've got this one, and we've got this one. And if we really go in, it's possible that you can tell a difference. Maybe these 2 are different. This peak and this peak right here might be different. Or it could be that these are kind of overlapping. But it's really hard to tell. You do see some separation. It would be nice to know what those integrations are to be able to tell what's what. Sometimes you can tell a difference and sometimes you can't. Just know that this is what benzene rings kind of look like, okay? So that's the reason why I'm showing it to you. You can have lots of things that are overlapping here, okay? I hope that helps you understand hydrogen NMR. I'll give a brief video as well on carbon NMR. It's not that different. Our numbers are a lot different, but it's not that different. I hope this helps. Thank you.